everyone. Today we're going to be talking about Gauss's law for AP Physics C, as Rosie the Riveter, apparently, because it is Decades Day today at school. Alright, I will write the equation for Gauss's law on the board, and we'll get started. Alright, so here we see that the total enclosed electric flux equals the total enclosed, or that the net electric flux equals the total enclosed charge. So here we see that you have the electric field times the dA vector, which we'll talk about in a minute when we do an example, equals the total enclosed charge over epsilon naught, and epsilon naught is just a constant. Alright, so it's useful in determining the electric fields due to charges, be they point charges, charges on a sphere, charges due to an infinite line, or electric fields due to an infinite line of charge. And this closed integral just means that it's measuring what's enclosed by that dA. And that dA can be pretty much anything you want it to be, although usually using cylinders and spheres helps us to capitalize on this Gauss's law. Alright, so let's talk about the most basic example, an electric field due to a point charge Q. Alright, so first we have our point charge Q. I'm going to make it a positive charge so that the field lines will radiate away from it. Alright, so now you have to put down what you would call a Gaussian surface. Now this is an imaginary surface, it doesn't actually exist. It just helps you to find that net electric flux, and then which helps you to determine the electric field. So I'm going to put one right, switch color. I'll put one right there. Alright, so that blue surface is the Gaussian surface. And it is at a distance r from this point charge. Now, you see how each of these field lines is radiating away from that point charge? Well, the angle that they make with this Gaussian surface is called the dA vector. And as you can see, if we zoomed in really, really close, this would be making a 90-degree angle with it, which is good because cosine of 0 is 1, and the dA vector is making a 0-degree angle difference with this electric field line, and so the cosine of 0 is 1. Doesn't screw up our equation and make one side equal 0, and that's always a good thing. So I will draw that in green. And you can see right here the comparison between the green and the red. That's a 0-degree angle difference. Alright, so now I can rewrite our equation, because that's what we'll be using. Alright, so now we have the electric field, which is what we're trying to solve for, times cosine of 0, because like we said before, 0-degree difference, times 4 pi r squared. And that's the surface area of a sphere, which is what our Gaussian surface is, because this is only a 2D drawing. If it was 3D, there would be arrows coming out at you and going into the board like that. So our Gaussian surface is a sphere, surface area of a sphere, closed integral, makes sense. And that's going to equal the total enclosed charge over epsilon naught. Alright, so as a result, when we solve for the E vector, or when we solve for the electric field, this cosine of 0 goes away because it just equals 1. Doesn't change our multiplication. And we divide by 4 pi r squared, and we get that the electric field equals the charge enclosed. And we could call this charge Q, and then it would just be Q, over 4 pi r squared times epsilon naught. And this is the electric field due to a point charge. Alright, let's try doing an electric field due to an infinite line of charge. In this case, we have to use a different Gaussian surface, because the best way to capitalize off of this being, the best way to capitalize off of using the cosine would be to use a cylinder. So I'll draw that out for you right now. Okay, so here is our infinite line of charge, that little box right there, and I'm going to draw a lot of little pluses in it so that we can show that this is a positively charged infinite line. And you're going to have to use your imagination and just know that it extends either way off into infinity. Alright, so the best Gaussian surface wouldn't be a sphere. It would probably be a cylinder, because that's the best way to go around this. So I'm going to draw in, oh, you know what? I'll make it easy for you. I'll use the same colors I used over here. Alright, so our Gaussian surface is now a cylinder. Now, we have, as you can see, we have 3 surfaces that it can make flux angles with. So this one, this circle right here, that's surface number 1. This whole long part of the cylinder is surface number 2. And then this other circle is surface number 3. All right. So, we have our radius, r, and that's how far away this Gaussian surface is from the line of charge, so that's r. We have, let's see, we have our electric field extending from it. And you know that it goes and then all the way through the page and back up. We'll draw that in 2 places, but it's really all over the cylinder, or really all over the line of charge. And on the ends, since they extend off into infinity, there's no n vector that's pointing this way, and no n vector on that side that's pointing that way. They're still pointing just up and down, never to the left or right. Okay, so, the best way, oh, and we can draw a flux angle, again, like we did here. We see that the dA vector, again, here makes a cosine of 0 with the electric flux, arrow, but over here it would make a cosine of 90 because the surface of the Gaussian surface is pointing this way. So this is the way that our dA vector would be pointing. And then our electric field line, like I said before, would still be pointing straight down. So here the cosine is 90. The easiest way to determine the charge, since it's an infinite line rather than just a point charge like we had here, is to define the charge in terms of density. So we can use, let's see, I'm going to switch to green now because my red marker's dying. We can switch to lambda, and that's the charge density. And like you might have guessed, it's the charge, Q, per unit length. And we can manipulate this so that it equals Q or it equals L, but this is the way that you would write density, just like the density of an object is mass divided by volume, charge per unit length. Okay. So now we can write our Gauss's law. We know what we're doing. And now we have three surfaces. Here, we just had one uniform surface, but here we need three different integrals because we have three different surfaces. It's not as bad as it sounds because two of them end up going away. So we can deal with surface 1. So we're talking about the electric flux in surface 1 times the dA, or dot the dA. That implies that you need the cosine there. And then plus surface 2 dot dA plus surface 3, right there, times that electric field, I'm sorry, I forgot to include that here, dot dA. And that's going to equal the total enclosed charge over epsilon naught. We just took this and we split it into three different parts. Alright, so like we said, for this middle part, or we'll start with surface 1. For surface 1, the dA makes the dA vector makes a 90-degree angle with the electric flux, with the electric flux vector. And so the cosine of 90, because it only matters, the parallel components are the only ones that matter, like you saw here, and like you're going to see here. So this cosine of 90 equals 0. So this entire piece is 0, and it just goes away. Here, the cosine is 0, because there's no difference in angle between these two. And so that we need to keep, because we're going to deal with that later. And then for surface 3, it's the same deal as surface 1. The dA vector is going out like this. The E vector is going down, just like over here. And that makes a cosine of 90, which of course equals 0. So this surface 3 also goes away. So now we just have that the surface area of unit 2 times the dA vector equals the total enclosed charge over epsilon naught. Alright, so here we have E times cosine of 0, which just equals 1, times the closed integral dA equals the total enclosed charge over epsilon naught. So, let's see. Okay, so now we need to rewrite this as the surface area of a cylinder. So we're doing surface area of a cylinder minus the two caps, because like we said, those don't count. All right. So we have E times 1, which is cosine of 0, times 2 pi RL where the radius is the distance away from the Gaussian surface. Usually the problem will tell you where that needs to be. The length is the length of the infinite line of charge, which is infinity, but eventually it goes away because we cancel it out. And yeah, so that's the equation for the surface area of a cylinder. And then, let's see. And then our density formula, which we wrote here, we can manipulate that so that instead of having lambda equals Q over L, we have Q equals lambda times L. Just multiply those two together. And so we can rewrite that. Ooh, got a little squish. Lambda L over epsilon naught. And so this is just another way of rewriting the original Gauss's law. And then you divide both sides by 2 pi r L because you want to isolate E by itself. The 1 goes away. Anything multiplied by 1 is itself. And so you get E equals lambda over 2 pi epsilon naught R. And that's the electric field for an infinite line of charge according to Gauss's law.